Egypt is located in the northeast corner of Africa. It is 3 times the size of New Mexico. It is divided into 2 regions, Upper Egypt and Lower Egypt. In Upper Egypt, you can find some of the historical wonders of the world, including the Great Pyramids and the Sphinx. Both of these features were built during ancient Egypt times. The pyramids were built as tombs for the dead kings and queens. Most of them are over 4,000 years old. They were built at a time when Egypt was one of the richest and most powerful civilizations of the world. Egypt is close to the Mediterranean Sea and the Red Sea. At the heart of Egypt is the Nile River. Without the Nile, Egypt would be nothing but desert. Everybody lives along the Nile because it is their only source of water. About 80 million people live in Egypt. Because the population is growing, resources are running low. 90% of the people in Egypt are Muslim. They follow the Islamic religion. In ancient Egypt, they believed in multiple gods. The king of Egypt was called the pharaoh. When a pharaoh died, their body was mummified. The pharaoh's mummified body was then placed in a pyramid. Egyptian people have always done lots of farming. Their children help out a lot. Today in Egypt, kids go to school every day. In ancient Egypt, only boys got to go to school. Nowadays, girls get to go too. Egyptian kids love to have fun. They hang out with friends, and play games and sports just like you. Egypt is a beautiful place. You should come visit sometime.
Elastic potential energy, gravitational potential energy, and the GPE, the gravitational potential energy equation, you're going to need to know what all those variables mean. So there are 2 types of mechanical potential energy associated with position. So mechanical potential energy is all about position of the object. So you change where the object is in space, which causes it to gain energy. So the first one that we're going to talk about is the elastic potential energy. So elastic potential energy. Now, we're just going to kind of mention this in passing because we're not really going to measure elastic potential energy for the first version of this course. But as you can see, the bow here is bending, and when he releases it, it will shove the arrow and release that energy into a forward motion. That is the elastic potential energy of that bow. Now, the primary mechanical energy, mechanical potential energy that we run into has to do with the Earth and the amount of mass the Earth has. So the Earth is pulling everything towards its center of mass. And at the surface of the Earth, that is around 9.8 meters per second per second. And that is called the gravitational potential energy. Now that gravitational potential energy, when we are calculating it, we're usually doing it from some frame of reference, usually the ground. Now the elastic potential energy, think about that like a rubber band. When I stretch the rubber band, so when I deform the rubber band and I add energy to it through my body, I stretch it out. So when you stretch that rubber band out, that adds energy to it. And when you release it, the rubber band flies, and everybody has a fun time shooting rubber band. So that's how I would like you to remember elastic potential energy, rubber band energy. The primary form of energy that we're going to focus on in here has to do with height. This image isn't as clear as I had hoped it'd be. This is a shelf, and then you have an orange with a bunch of clothes on it sitting on this shelf. And this orange with a bunch of clothes is relative to some position, and we're going to just say that position is the ground. And so the gravitational potential energy, we're going to refer to that as GPE. The gravitational potential energy of that object relative to the ground is based on the equation GPE is equal to mgh. So when we're calculating our potential energies, we are always going to calculate using mgh in here in this class because we're focusing all on GPE and the mechanical energy of GPE and how that interacts with KE, kinetic energy. So this first variable, the variable m, we've seen that before. That is the mass of the object, and that mass is in kilograms. H, since we're dealing with energy, we do have some sort of distance involved. This h is the height in meters from some reference point, usually the ground. But we could choose things halfway between the ground and someplace else. We just won't do that in this course. And then G. G. This G could also be written as big G. Why would I be able to write that as big G? Because that is the acceleration due to gravity. So the acceleration due to gravity, what's the unit on that? Meters per second. Or, as we've talked before, how else could you write that? Meters per second squared. So that is the equation that we're going to use in this class for gravitational potential energy, a part of mechanical energy. Thank you for watching. This has been Justin Higgins. Have a glorious day and be excellent to each other.
Space Scoop. Our galaxy, the Milky Way, is more than just a giant barred spiral containing hundreds of billions of stars. It's also the center of a colossal empire and rules over about 20 smaller galaxies that orbit around it, similar to the way our moon orbits the Earth. The shining stars and glowing arcs of gas in this picture reside in one of these subjects, a dwarf galaxy called the Small Magellanic Cloud. If you live in the southern hemisphere or near the equator, you may have noticed two bright but blurry clouds in the dark night sky. The smaller of these clouds is the Small Magellanic Cloud, one of the Milky Way's so-called satellite galaxies. It is a dwarf galaxy, meaning that it contains far fewer stars than galaxies similar to our own. While the Milky Way is made up of about 300 billion stars, the small Magellanic Cloud has just a couple of billion. On a cosmic scale, this galaxy is extremely close by. Moving at the fastest speed known in the universe, the speed of light, it would take less than 200,000 years to travel there from the Earth. Being so close to us, the small Magellanic Cloud offers astronomers an opportunity to study phenomena that are difficult to examine in more distant galaxies. This picture shows an area of the galaxy called the Wing. It contains 3 star clusters that astronomers have been studying recently to find out how young stars are born. Space Scoop is brought to you by NASA's Chandra X-ray Observatory and Universe Awareness.
We analyze light from light sources in the sky by splitting that light using a prism or gradient and then measuring how much of the continuous spectrum, the rainbow, is visible, measuring that light's wavelength, and also measuring the intensity of that light or luminosity. This is the measurement of black body radiation. Any object that is heated will produce light. If an object is kept at constant temperature, we can use that temperature to classify the object based on the intensity of that spectrum given off. A star's black body radiation is measurable because the star's radiation is fairly constant. There's some fluctuation, but the changes that stars undergo in their black body radiation is measurable as well and tells us even more about the star. We can imagine the radiation coming off a star by imagining that the photons leave the surface of the star equally. This idealization allows classification of stars based on their black body curves. And as originally it was based on the visible portion of the electromagnetic spectrum. Although we can now measure into other bands with lower energy than red light or higher energy than violet, for our purposes we'll ignore these non-visible forms of light in this explanation. A black body curve will measure the wavelength of the visible spectrum, Roy G. Biv, with red starting around 400 nanometers to violet ending around 800 nanometers. And the black body curve compares that wavelength with the intensity of the light, or luminosity. Think of a light bulb. When the light bulb is turned off, it has a low luminosity, but when the bulb is turned on, the luminosity increases. And when wavelength is plotted on a graph and compared to intensity, the temperature in Kelvin of the star can be measured and compared to other stars. And there is a pattern to how stars fit in the black body curve. Blue stars, which are very hot, peak in the color blue, and yellow stars, which are not as hot, peak with intensity in the color yellow, and the coolest stars, red stars, have an intensity that peaks around red. And we use this information to classify stars.
My name is Justin Higgins, Mr. Higgins to my students in real life. This course is about the fundamental understanding of the Earth's place in space and how our universe got here, how stars form, etc. It is a basic level astronomy course geared at the ages 15 to 16, based on concepts and understanding how the processes work. Very little math in this course. The videos contained within this course are designed to teach you the basic level knowledge and comprehension to be able to discuss the topics that we will cover at a higher order. One of the great things about video is that you can pause, rewind, and watch over again. And I would suggest very strongly for both my students in real life and those of you that would like to learn more about this material on the internet through my videos, that you follow the suggested note-taking method, which is the next video. And that will allow you to comprehend and understand the basic topics covered in this course, the concepts.